Hello students. So we just completed our course of quantum mechanics. Now I will start the revision procedure. Now first of all we will have a look at of the syllabus, and then we will take every topic into consideration and then try to understand exam according to examination point of view. So there will be many students who were just absent in the initial phase of our course, so they can also understand the topics from here on. So let's have a look at the syllabus. This is your syllabus. Okay, now in quantum mechanics we can see that the topic starts, the third section is the quantum mechanics, and here are the topics: that the quantum mechanics, failure of the classical mechanics, EM, electromagnetic theory, then quantum theory of radiation, old quantum theory, then the photon consideration and photoelectric effect, which was given by Einstein in 1905, for which he also got the Nobel Prize. Then we will discuss the Einstein photoelectric equation and also some quantum explanation of the particle nature of light. Then we will look at Compton effect, and Compton effect is the vivid confirmation of the particle nature of the light. And after this we'll discuss about inadequacy of the old quantum theory, then de Broglie hypothesis, and then the complete course. Okay, so let's have a look at the initial stage, that how the quantum mechanics could build up. So let's have a look on this. So first of all, you need to consider this book. This is Arthur Beiser 6th edition. I will give you the PDF of this. Now this is an extra mile in this quantum mechanics course. You can study by your local publisher or your normal books like Arch and for the B.Sc pass course, but this book will give you the brief explanation of the quantum mechanics and the modern physics or quantum theory, all these courses. Now if I say you that the quantum mechanics course is actually not the quantum mechanics course in your not the quantum mechanics course, because quantum mechanics starts from the Born approximation. However, quantum mechanics means quanta, explanation of everything by a packet of energy, or on the explanation of the concept, or every phenomena or every interaction by the on the microscopic scale. Then this theory starts from the Born approximation, and that's why we take two theories. One is old quantum theory and second one is our main quantum theory. Okay, so the course starts from the second chapter of this book. First chapter is special theory of relativity. You might have studied this in the first year, but this is not a relevant topic now. So first of all, we will discuss electromagnetic waves, then black body radiation, then photoelectric effect, and then we will discuss Einstein theory of photoelectric effect and Compton effect and so on. So first of all, the topic starts from electromagnetic waves. Now we are already discussed this in complete explanation. Let's start the this electromagnetic waves, electromagnetic radiation, or we can say photon. Okay, electromagnetic waves, EM waves, or we can say what light. So if anyone asks you that what is light, then the simple and only answer to this question is that light is electromagnetic wave. Electromagnetic wave in which electric field and magnetic field vibrates in the perpendicular direction to the propagation of motion of the wave, right? So there happens to be electric field and magnetic field, and these both of the things vary perpendicular to the direction of motion. If this direction is the direction of electric field, vibration of electric field is happening like this, and if vibration of magnetic field are happening in this direction, then both A and B are perpendicular to each other, and they are perpendicular to the direction of motion as well. Direction of motion, if this is the k vector, this is the okay. So that's why the nature of these waves is transverse. Now we know that waves are of two types according to their nature. One is transverse, second one is longitudinal. Okay. Transverse nature means the vibrating quantity, like here in this electric field and magnetic field, the vibrating quantity vibrates in the perpendicular direction to the propagation of motion, means they vibrate in the perpendicular direction to the propagation of motion. But in the longitudinal wave, the vibration of the vibrating quantity is in the same direction of the propagation of motion, for example sound waves. Okay, so why we are discussing this? Actually we need to focus on light, because light has all the explanation behind quantum theory and classical theory. You can study, because many kind of interaction using light. Okay, so first of all, let's see according to this book. Now you need to focus that the debate that light has particle nature or the wave nature, this actually started in the early or the 1650, after 1650, when Newton gave his corpuscular theory. Okay, according to Newton, when Newton in his book Optics, this was the book name, and he suggested that corpuscular theory of light in I guess near about 1658, I guess. Okay, so according to this theory, that light is actually a beam of particles, and particle with different properties means the particle having different color composition, and that in wave theory we can say those property, we can signify those property using wavelength and frequency. Okay, so every particle has a different kind of property, and that property distinguishes them from each other. Like the particle after dispersion, if they give like red color, in dispersion effect we can see that white light focus when falls on a prism, that light get dispersed by the prism medium, and there are 7 color composition. Okay, so actually in corpuscular theory he explained this phenomena: dispersion, reflection and refraction. So there are initially in light there are two theories got developed. First one is ray optics, and second one is wave optics. Okay, this is not in your course, but for the formalism of this course you need to focus on these topics. However, this is not much important according to your examination point of view. So just focus on this. The ray optics. In ray optics, we study the phenomena like refraction, reflection, and dispersion, and so on. In wave optics, we study the phenomena like interference, like diffraction, and polarization. What is happening to this pencil? Polarization. Okay. So in ray optics, he explained diffraction, reflection, and dispersion, all these phenomena using his corpuscular theory. Then came the Huygens theory and the theory of wavefront. And Huygens explained that the particles or the secondary wavelet source traveling within the same phase are on the same wavefront. And he explained these phenomena using wave theory. Okay. So, according to Newton, light is a beam made up of particles, but according to Huygens, light is a beam of waves, or light is the composition of wave, in which now, so far, so nobody could explain why light is traveling in vacuum. Okay. And initially nobody knew the composition as well, that light is made up of what, or light is an electromagnetic wave or not. Then came Maxwell in 1855. Then came Maxwell in 1855. In 1855, however, they were, we can say a milestone got achieved in 1801 and 1816 when in 1801 interference phenomena was discovered by Thomas Young. In 1801 he explained interference using double slit experiment, and then 1816 Fresnel explained his theory of the diffraction using the Huygens theory, or the explanation of Huygens. Then to discover that, okay, so far Newton was also right, and this Huygens theory and Young Thomas these theory were also right. But the main explanation come in 1801 when using the wave theory or wave approach, Thomas Young could explain that why light is cutting out light itself when they superimpose on each other. If two waves are superimposing, one wave has a particular displacement define something like this, and second one is with the same frequency, phase difference, and the same amplitude. When they made to superimpose, the superimposition was something like y1 plus y2, and actually this came out like r sine omega t and some phase. Okay, so now this thing, from here on we can see that the interference composition or the phenomena on the screen was something like this: when two waves or the wavefront got divided by a double slit text. Okay, so the main intensity spectrum on the screen was something like this. And why this is happening, that at some certain points we are getting minima, and at certain points we are getting maxima positions. Okay, so to explain this, we can take this wave approach, and wave approach explain this, because particle nature does not explain this. A particle beam is coming out from here, particle beam is coming out from here, two particle beams are coming out from different holes, then they must fall on something like this, that there should be a collection of particles here and there should be a collection of particles here. There should be no distribution of the particles, and with the particular kind of approach, particle distribution should not be from in this direction and this direction as well. There should be no particle distribution in this way. So to explain this phenomena, he took wave approach, and simply the vector addition of wave the vector addition of wave can explain this. Okay, so this was a milestone in this theory when Thomas Young actually explained that light is or the light is has wave nature. Okay, then Fresnel theory also made a stamp on this, that light is actually wave. Then came the in 1855, that if now the question arises, everybody put up a question, that if light is has the wave nature, then how can light travel through the vacuum? Because to for a wave to travel, it requires a certain kind of medium, right? So how can light travel through vacuum, because vacuum is not a medium? Then came the 1855 Maxwell, and he made a significant contribution substantially in this course, this theory. He explained that using the four laws of electric field and magnetic field, the Gauss law of electrostatics and Gauss law of magnetostatic, Faraday law, and the last one modified Ampere's law, he explained that light is an electromagnetic waves. He used four equations, his Maxwell equations, and then using those equations, like first equation is Gauss law of electrostatics, which is del dot E is equal to rho upon epsilon naught. Okay, second equation is del dot B is equal to 0. Third equation is del cross E is equal to minus del V by del T, and fourth equation is del cross B is equal to mu naught J plus mu naught epsilon naught del E by del T. Okay, now mu naught and epsilon naught are the constant defined for vacuum, and in vacuum rho is equal to 0 and J is also 0. In vacuum, rho and J are 0 because charge density in vacuum is 0, as there is no medium, and current density is 0 as well. So using these four equations, now these equations are coupled. If we change in magnetic field, then there is a significant induction of electric field. If we do change in electric field, then there is a significant induction of the magnetic field. Now using these four equations, he actually articulated that electric field vector can be, or he brought up an equation, he solved this, and he actually explained that del square E is actually 1 by mu naught epsilon naught del square E by del T square. Now what is this? Now this is certainly an equation of wave. Okay, any wave quantity we discussed in our course, that in the last lecture when we were studying Schrodinger equation, we discussed wave equation as well and wave function. So for any wave quantity to propagate, you need a wave equation to explain that, the propagation of, or the evolution of that wave function with respect to time and space. You need wave equation. Now this is kind of a wave equation. This is a wave equation in which the electric field propagates with this velocity. The velocity of this, the propagation of this function, electric field, is, now this is for the any wave equation in which A is the wave function. This is the wave equation actually. When you compare both of the equations, then E is the wave function here, and the velocity comes out to be mu naught and epsilon naught. When you put the value of mu naught and epsilon, mu naught is 4 pi into 10 raised to power minus 7, and epsilon naught is 8.854 into 10 raised to power minus 12. When you put these two values, the velocity of this wave comes out to be 2 into 9.2.998 into 10 raised to power 8 meter per second, and this is the same value of velocity of light c. From here on, he contributed in this. Maxwell contributed, and Maxwell actually articulated that the light is electromagnetic wave, because similarly you can have equation for magnetic field, and E and B both are perpendicularly vibrating to the propagation of motion of this wave. Then he actually explained this. यार वीडियो कटेगी क्या ये? Okay, sorry for disturbance. So he articulated that electric field and magnetic field both vibrates in the perpendicular direction to the propagation of this wave. Then the theory got a stamp that actually light is electromagnetic wave in which electric field and magnetic field vibrates in the perpendicular direction of the motion, and the velocity of light comes out to be this. And then we got significant measures in this theory that actually light has the wave nature, not the particle nature. But after only 50 years, now there was another theory, photoelectric effect and Einstein approach with using the Planck's hypothesis, and we will discuss that in the next class. Okay.